Okay, so in this video we're going to go over what are defined as our hyperbolic functions, which we'll see are really just a sum and difference of exponentials. And these show up really in what's called the catenary problem. So if you look here, the catenary problem is really just if you kind of have a chain that's kind of suspended across 2 points, the way that it kind of hangs, that that curve that you see here, that is a hyperbolic function. All right, so we're going to set to define our hyperbolic function. All right, so we're going to use this notation, cosh, and the way what that is shorthand for is the hyperbolic cosine. So you'll see they have a lot of names and similar properties to our trig functions, not quite exactly the same, but there is a bit of a kind of relationship into how they're kind of derived. All right, so the hyperbolic cosine is defined as e to the x plus e to the negative x over 2. The hyperbolic sine or sinh of x is e to the x minus e to the negative x over 2. And then my hyperbolic tangent of x is sinh x over cosh x. Okay, and then here, taking the ratio of those, we get the 2's cancel out, plus e to the negative x. All right, and then similar, our hyperbolic secant of h of x is just 1 over the cosh, so it's 2 over e to the x plus e to the negative x. All right, and a hyperbolic cosecant of x is 1 over sinh of x, and that is 2 over e to the x minus e to the negative x. And then our hyperbolic cotangent of x is just 1 over its cosh x over sinh x, or 1 over the tangent. So that is e to the x plus e to the negative x over e to the x minus e to the negative x. So those are the definition of our 6 hyperbolic trig functions, right? In this section, really I just want to focus on how to derive the derivatives, and then as you'll see, the exercises is really just more practice on our differentiation rules. Now we just have new functions that we can practice them on. Right now, the derivatives, as you see, there's nothing more than derivatives of exponentials, which we have learned to do. Right? So I want to take, for example, let's say the derivative of the hyperbolic cosine of x, right, which is the derivative of the definition of the hyperbolic cosine is this. Okay. And again, exponential, the sum rule, the divided by 2 is a constant, so you can just rewrite it with that in there. So here, e to the x, this derivative of e to the x, e to the negative x, the derivative is negative e to the negative x, all over 2, right? And then we can see that that is actually sinh of x, the hyperbolic cosine. Okay, so you'll start to see kind of some similarities between the trig derivatives, and here are hyperbolic function derivatives, right? And here I'll state this without proof, although I do want you to understand, like on your own, try to derive these using the properties here of exponentials, in particular just the derivatives of them. So here, the derivative of sinh of x is going to be cosh of x, and then the derivative of hyperbolic tangent of x is going to be secant squared, hyperbolic secant squared of x, and then the derivative of this hyperbolic secant of x is negative secant of x, hyperbolic tangent of x, and then the dx of hyperbolic cosecant of x is negative hyperbolic cosecant of x cotangent hyperbolic of x. All right, and then lastly here, the derivative of the cotangent, hyperbolic cotangent of x is negative cosecant hyperbolic squared of x. Okay, now it doesn't quite like a one-to-one comparison with our trig, but kind of there's negatives in different places here. But you get the idea, right? And if these are the derivatives, then we do have also so we do have some integral formulas, right? So the integral of cosh of x dx is sinh of x plus c. The integral of sinh of x dx is cosh as well. The integral of my secant squared, hyperbolic secant squared of x dx is hyperbolic tangent of x. And again, don't forget the plus c. Okay, so that's 3. And then here, the integral of hyperbolic secant x, hyperbolic tangent of x dx is negative hyperbolic secant of x plus c. And then my integral of hyperbolic cosecant of x, hyperbolic cotangent of x dx is negative cosecant hyperbolic of c plus c. All right. All right, and lastly here, I have the integral of hyperbolic cosecant squared of x dx is equal to my cotangent hyperbolic of x plus c. All right. Okay, and again here really is we have the formulas, so just make sure you can apply them and make sure that you can derive, like if given a problem that says prove the derivative of the hyperbolic tangent is secant squared, right? Then you can use the exponential form to derive that formula.